Here's your poser for today. Coin A is thrown up in the air at a speed v from a height of h. Coin B is thrown down at the same speed from the same height. Which coin hits the ground at the highest speed, neglecting air resistance? And your choices are coin A, coin B, they hit the ground at the same speed, or it can't be determined. The answer is that they hit the ground at the same speed. Now, if you find that surprising, you need to remember the law of conservation of energy. Consider at first not the direction in which the coins are going. Consider only the energy that the coins have. So coin A is moving upward at a speed v from a height h. Its kinetic energy is 1/2 mv squared, and its gravitational potential energy is mgh. Coin B is thrown down at the same speed from the same height, so its kinetic energy and gravitational potential energy are the same. It doesn't matter which direction they're going. Now both of the coins eventually will hit the ground in the same spot, and all of their energy will have been converted into kinetic energy pointed down. If you believe in the law of conservation of energy, they have to hit at the same speed, otherwise their energy would have been different at some point during the experiment, and obviously it can't be due to the law of conservation of energy. So they hit the ground at the same speed. Now if you don't believe that, feel free to pull out your kinematics toolkit and do the math. But what you'll find is that coin B will go up into the air, coin A will go up into the air, stop, come back down, and pass the same point, going the same speed it was down that it was going up. So it'll wind up in the same state as coin B after it's gone through its arc. Okay, I'm Mr. McBrien. This is SPH3U, Efficiency and Energy Loss. The Ontario curriculum states that students will identify qualitatively the relationship between efficiency and thermal energy transfer. And that's what we're going to do today. Maybe we'll slip in a little quantitative as well. Okay, so we'll start with a review of power. Then we'll define efficiency and talk about how to calculate it. And finally, we'll talk about why it's often depressing to be an engineer, and sometimes a philosopher too. We'll talk about the 3 laws of thermodynamics. Okay, power. We've talked about this before. It's the rate at which work is performed or energy is transferred, and it's simply work divided by the time over which that work is done. And it has units, of course, of joules per second, which is the same as watts. Let's do an example of how we calculate power. Let's imagine a motor does 320 joules of work over an 8-second span. The power of the motor can be easily calculated by using our power expression. It's the work done divided by the time required. In other words, 320 joules divided by 8 seconds, which means it's 40 joules per second, or 40 watts. And of course, we can rearrange that equation when we need to, or even use other expressions when we have to. So let's imagine a slightly more complicated problem. A person lifts a 35 kilogram bucket of bricks to a height of 10 meters using a pulley, doing work at a rate of 87 watts, or 87 joules per second. How long does it take? So in this case, we need a little more work to find our answer, because we don't know the work up front. We have to calculate the work by using the eventual gravitational potential energy of the bricks to calculate how much work the person did. So we use mgh, so 35 kilograms times 9.8 meters per second squared times 10 meters equals 3.43 times 10 to the 3 joules. And notice that I carried one extra significant figure because this is not yet our final answer. Okay, next we need to rearrange our power expression to solve for delta T. And of course, by multiplying both sides by delta T and then dividing by the power, we get delta T equals work over power. And then from there, this should be divided by 87 watts. 3.43 times 10 to the 3 joules divided by 87 watts gives us 39 seconds. Now, no motor is actually 100% efficient. And it's a good time for us to discuss efficiency. Efficiency is the ratio of useful energy or work output to the total energy or work output. No great shock, and we express it typically as a percent. So, when we look at the ratio of the useful to the amount of input energy we did, multiply it by 100%, we get our answer. An easy example: a model rocket engine contains explosives storing 3,500 joules of chemical potential energy. We want to calculate how efficient that rocket is. If it puts a half-kilogram rocket to a height of 1 times 10 to the 2 meters, or 100 meters. Well, what we can do is use our expression for gravitational potential energy to calculate the output energy from the height, 490 joules. And then from there, we just divide the useful output, 490 joules, by the output, 3,500 joules, and we find that the rocket was 14%, had 14% efficiency. Our second example: a 120 watt motor accelerates a 5 kilogram mass from rest to a speed of 4 meters per second in 2 seconds. And in this case, we can use the kinetic energy to calculate the useful output of the motor, in this case 40 joules. And then from there, we can calculate the input energy by multiplying the power times the time and get the amount of input energy, 240 joules. To get the efficiency, we simply divide 40 joules by 240 joules and find that the motor was 17% efficient in this case. Now, we can take a second approach to this. We could have calculated the useful power output and made that a ratio of the power input. And of course, delta T cancels in both cases. So if we take that approach, our power input was 120 watts, that's the rating for the motor, and all we have to do is calculate our power output, and that is just our kinetic energy divided by the time, and we get 20 watts. And 20 watts over 120 watts is, once again, 17% efficient. So if our motors and our systems are not 100% efficient, where does the extra energy go? Well, no great shock. That energy is lost in various non-useful forms of output. Typically, heat and sound, vibration, all kinds of less useful output from those systems. And this leads us to a rather unhappy set of truths, the 3 laws of thermodynamics. The first law: you can't win. The second: you can't break even. And the third: you can't even get out of the game. So what do we mean by that? Well, you can't get something for nothing, Energy can't be created, it's always conserved. You can't break even. Unfortunately, you can't even return to the state at which you started. We talk all the time about zero friction systems and things like this. The truth of the matter is you can't get back to the state you started. Some energy is always converted to non-useful forms. And another way of looking at this is that disorder or entropy of a system is always increasing. And finally, you can't even get out of the game. There's no state at which no energy is ever lost except at absolute zero, and we can't really attain this temperature with any reasonable system. So unfortunately, we're stuck in the real world where these rules apply. Okay, and on that happy note, here's some more practice. Please go ahead and read up on this and do the questions noted here. Thank you and have a great night.